Okay. So in the previous session, we have seen what are equivalent matrices and similar matrices. And then we introduced what are affine spaces. So let us quickly recall equivalent matrices and similar matrices, and then we will continue with affine spaces. Okay. So equivalence of matrices, you remember, this is for any rectangular m by n matrix. So two matrices A and B of same order are said to be equivalent if there exists invertible P and invertible Q such that this condition is satisfied. And we saw that this is an equivalence relation. That is, it is reflexive. A is equivalent to itself. Symmetric. A is equivalent to B implies B is equivalent to A, and transitive. A equivalent to B, B is equivalent to C implies A is equivalent to C. Right? And we saw that in the specific case, when P and Q are, when A and B are matrices representing the same linear transformation, then we have a specific way to find P and Q. So for a transformation T from V to W, if beta 1, beta 2 are two ordered bases of V and gamma 1 and gamma 2 are two ordered bases for W, and A is the matrix representation of T with respect to beta 1 and gamma 1, and B is with respect to beta 2 and gamma 2. Then these two are first of all equivalent, and we can find this A, B, P, Q, everything in the procedure mentioned here. We have seen example also how to do this. We have seen some examples, right? Similarly, so here are some characterization of equivalent matrices. So two matrices A and B are equivalent if A can be transformed into B by a combination of elementary row and column operations. So two matrices A and B are equivalent if rank of A is equal to rank of B. So this is the most general method to verify equivalent matrices. Rank of A is equal to rank of B. If this is true, then we know that A and B are equivalent, right? And we have defined similar matrices also. So the main difference is that here we are considering only square matrices. Okay. So here two matrices A and B of order n by n are said to be similar if there exists an invertible matrix P such that B is equal to P inverse AP. Okay. So we check similarity only for square matrices of same order. Okay. So this also defines equivalence relation, and similarity implies equivalence. And we have seen this example to show that if two square matrices are equivalent, that does not imply they are similar. Here these two, here we know that rank of A is equal to rank of B is equal to 1, is equal to 2 in both the cases. This means that A and B are equivalent, right? A and B are equivalent, but not similar. So it is not similar. We have done the proof already. Okay. So here are some other properties. So if A or B, either one is invertible is sufficient to say that AB is similar to BA. Okay. And if A and B are similar, then A power n is similar to B power n. If A and B are similar, again the transposes are also similar. Okay. And similarly, here also we see that we can say two matrices representing the same transformation with respect to the same basis. So T with respect to the basis beta for both the domain and codomain. Similarly, T with respect to gamma for both the domain and codomain. So these two matrices are similar. And here are the technique to find what is A, B, P, and Q. Okay, fine. So some other properties. So if two matrices are similar, then they have same rank, same trace, and same determinant. So what about the converse of the statement? If two matrices have the same rank, same trace, and same determinant, can they be similar? No,
No.
right? We have seen this example. So this matrix have same rank, same trace, and same determinant. But as we have seen the same example, so they are not similar matrices. Okay. So this is what we have seen in general about equivalent matrices and similar matrices. Okay. So the next topic is affine subspaces and affine mapping. Okay. So what are affine subspaces? We have seen that. So given a vector space V, an affine space of V is a
Ma'am,
subset L. Remember, it is just a subset,
hello,
not a
ma'am.
subspace. Yes.
Ma'am, actually,
Ma'am, actually, I have gone through with the lecture
Hmm.
from the portal, but I haven't cleared the concept, this affine subspaces. Can you please explain it in details
Yes, yes. In detail,
with
we are
one
going to see
example
affine
only?
subspaces today.
Okay, thank you, ma'am. Thank you.
Okay. So an affine subspace of V is a subset L. Okay. So V is a subset of L is a subset of V. Okay. So such that there exists a V in V and a vector subspace U of V such that L is equal to V plus U. Okay. So here you see that V plus U means the set of all V plus small u where U are elements of the subspace U. So any affine space, you can look, so think of it as a translation of a subspace. So U is a subspace of the vector space V and V plus U means it is a translation, right? So any affine space can be thought of as a translation of a subspace. Okay. So graphic or geometrically, you can see that they are objects that are parallel to a subspace. So here are some examples. You can see here in R2. So the red line is your y is equal to x. Okay, so this is your y. This is the line y is equal to x. Is this a subspace? It is passing through origin,
Yes, it is.
right?
Yes.
So it is a subspace. So now, what about this green line? It is passing through which point here?
No. Mm. One
1
comma
comma 0.
0.
1 comma 0. But is it passing through the origin?
No.
No.
No. You also observe that this line is parallel to y is equal to x. So this is a affine subspace, right? So any line parallel to lines passing through origin, they are all affine spaces. So here you see the red line is a subspace and the green line is a line parallel to this subspace and hence this is an affine space. So how can we see this? So according to the definition, if I'm calling this, let us say this is L1 because I have another line L2. Okay, suppose this is L1, this is L2 and this is my U. Okay, so now how can we write this L1 in terms of U? L1 is, I can take any entry in fact from L1. So maybe I can take this for now. So if I'm taking 1 comma 0 plus the set of all x comma x such that x is in R. This is your U, right? This is your U, right?
Yes.
So now what is this set?
Yes, ma'am.
This set is nothing but set of all x plus 1 comma x such that x is in R. Do you agree? Yeah.
Yes.
So for example, you take this point. What is this point? This point is 2 comma 1, right? So this is 3 comma 2. So all the points are of the form x plus 1 comma x, right? So you see that the green line here is y is equal to x. Can you tell? Minus 1, right? Y is equal to x minus 1 because here you see that here x plus 1 is there and here x is there. So y is equal to x minus 1, right? And what about the equation of this line L2? Can you tell? See, it is passing through, what is this point here?
0 comma 2.
It is passing through 0 comma 2. So can you tell me what is this equation of this line?
X plus 2.
Y
X
is
plus
equal
2.
to x plus 2, right? So now you see that this is also a line parallel to this subspace U, right? And can anyone tell how to write L2 in this form, right? We have written there. So L2 is
x minus 1 is
0 comma 2
0 comma 2
plus
plus U. So this is your U, right? So if I'm adding 2 to the second entry, then this becomes set of all x comma x plus 2,
plus 2.
plus 2.
right? So now look at this definition. So this is your V, this is your U, and this is your V and this is your U. Okay, so you can observe that The affine spaces are nothing but lines parallel to this subspace U. Okay, so this is to understand what are affine spaces in R2. Okay, in general, here we should note one thing: any subspace is also an affine space. So now this U is also an affine space. Why? Because I can write U as 0 plus U. So now 0 is my V, right? So then 0 is equal to U is equal to 0 plus U means I can consider this also as an affine subspace. Okay, so any subspace is also affine, but the other way is not true. Affine spaces need not be subspaces. Okay, clear?
So
Yes.
in R2,
Hmm.
all the lines are a affine space because it will be parallel to some lines that pass through origin or
Exactly, exactly. So if you see that, what is the general equation of a line? So you know that y is equal to mx plus c, right? So you know that y is equal to mx plus c is always parallel to y is equal to mx, right?
yeah.
So you know that any line with this kind of an equation, it is a affine space in R2. Okay, we will see in more detail like what other possible affine spaces can be there in R2. So just to understand geometrically, I have given this example here. Okay, so let us look at the same scenario, similar scenario in R3. Okay, so now you have x, y, and this is z. Okay, so now what is this plane representing? This one here is kind of
XY.
like some kind of
XY.
yellow. XY plane. So this is your XY plane. And you see this plane in violet and here in green, these are planes parallel to this XY plane. So this XY plane is first of all a subspace, yes or no?
Yes.
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 So this is a subspace. So now in this scenario, this is my U. This XY plane is my U. And this is my L1 and this is L2. Okay. So here, yes, L1 and L2 are parallel to this subspace U. So L1 and L2 are affine spaces. Okay. So now we should be able to write this L1 and L2 also as V plus U. Yes or no?
Yes, ma'am.
Yes.
Yes. So now for maybe it is not very clear, but let us say that it is passing through this point. So this is 0, comma
0,2.
2.
0,
0,
comma 2.
2.
And here this is 0, comma
0,
0,
minus.
0
minus.
minus 3.
okay. So now you see that L1 I can write it as 0, comma 0, comma minus 3 plus U. And L2 I can write it as
0,
0,
0,
comma 0,
0,
comma
2
2
plus U.
plus U. Right? So here what is our U? Your U is set of all x, comma
Y, 0.
y, comma 0. Right? So here that is 0. X, y in R. So what is your L1 then? L1 is set of all x, comma y, comma
minus 3.
minus 3. X, y in R. And L2 is set of all x, comma y, comma
X,
2,
2.
x, y in R. Okay. So you see, they are translations of subspaces. When you can view geometrically, in all scenario, you may not be able to view geometrically. But as far as we are able to view geometrically, you can observe that they are parallel to some subspace. Okay, the affine spaces are parallel to some subspace. So in fact, they are exactly translations of some subspace. Okay, so affine spaces are thus translations of a vector space of V. Okay, so if V is equal to 0 belongs to V, then L is equal to 0 plus U is equal to U. This implies that every vector subspace is also an affine subspace. Okay, so every vector space is also affine space. So that is what I mentioned here also. So for example, here I already told this U is also an affine space because I can write it here in this way. Same here also. I can write as 0, 0, 0 plus U. So here this is also an affine space. Okay, fine. So
Yes,
here
ma'am.
is an example. Consider the vector subspace U is equal to set of all x comma 0 such that x is in R of the vector space V is equal to R2. So in R2, so what is this U? X comma 0 means what is that? It is the
Origin.
what origin?
X-axis.
X-axis. X-axis.
It is the x-axis, right?
Yeah.
So this is your U, right? So your x-axis is U here,
Subspace.
Subspace.
right? So now this is a subspace. Okay. So now let us take this element V is equal to 0 comma 1. So 0 comma 1 means maybe somewhere here. Okay. So now we are defining L as V plus U. So that is set of all 0 comma 1 plus x comma 0. So it is set of all x comma 1. So it is this line, maybe some other color. I don't know. So let us say it is this line.
Affine.
So this is your L, right? So this point is 0 comma 1. Now you see that here all the points are of the form x comma 1. Okay. So this is your L. Okay. So now you see U is a subspace and L is an affine space. Right? Is that clear? Yeah.
Yes.
So the point here to be noted is that V is not unique. Okay. So here instead of, for example, we first considered 0 comma 1. If I'm taking some other element of L, for example, if I'm taking 2 comma 1, then what happens? Then V dash plus U is 2 comma 1 plus x comma 0. It means what? X plus 2 comma 1. So is this set same as this set? Are these two set equal? Right? These two are equal, right? Because x is varying over R in both
Yes,
the
ma'am.
scenarios. So these two sets are same. So this V in this representation of L is not unique. Okay. So any vector in this L is of the form a comma 1. So if you put a comma 1 in general also, you can see that the set is not changing. So what is that we observe? For any affine space L, which is equal to V plus U, you can see that the vector V is not unique. Okay. In fact, V can be any vector from L. Okay. So if U is equal to 0, then what happens? If U is equal to 0, then what happens? Then L is equal to just V, the singleton V. And V is unique in this case. Only in this scenario, when your U is the 0 space, only in that scenario, your V is unique. Because it is the only element of L. Okay. If this is not the case, then V is not unique. How to see this? Okay. So let us say that you have, let us say you have L is equal to already V plus U. You already have L is equal to V plus U. Okay. Now let us say you take another element, maybe we call V dash from L. So V dash, since it is in L, we can express it in this form, right? So how can we express V dash? Can you tell? V plus
U.
some element of U. So maybe I call that
Small
as U
u.
dash. Okay. So for some U dash in U. This is okay, right? This step. Yeah. So I have
Yes.
taken some element of L and I have expressed it in this form V plus U. Okay. So here U dash is an element of U. Now you should observe that V dash minus V is equal to U dash and this is an element of U. So in general, you can observe that the difference of any two element in L is an element of U. Okay. But here that is not what we need. Here we want to say that the vector V is not unique. You can put any vector, any V from L and you will still get L is equal to the same space. Okay. Okay. So now according to our definition, L is equal to V plus U, which means that V plus U where u belongs to u. Right? Now, I am simply going to add and subtract this term v dash. So I'm just adding v dash and subtracting v dash. Okay. So now here what I have done, I have added and subtracted v dash. Okay, here. That's all I have done. Nothing new. So here, what do you know about v minus v dash? Where does it belong to? V dash minus v belongs to u. So v minus v dash also?
Belongs to you.
Yeah. So v minus v dash belongs to u. Your u belongs to u. So this implies u plus
You.
v minus v dash belongs to u. So this entire term now belongs to u, right? So this entire term belongs to u, right? So I can rewrite this as v dash plus maybe some u double dash where u double dash belongs to u. Okay. So now this means I have written this as v dash plus u. Okay. So the same L I have written as v dash plus u. Okay. So what is that you can see? You can see that you take any element from L, then you will be able to express this L as that v dash plus u. Okay. So this v is not unique in this representation. Okay. So is this clear? That v is not unique. We have seen that in this example also, and here we have seen the proof as well. Is that clear so far? Yeah.
Yes, ma'am.
Yes, ma'am.
Okay. What about this u? What do you think about this u? Is that unique or not?
Yes, it is.
So, so far in the examples we have seen. So for both this L1 and L2, do you think there is any other subspace which is parallel to L1 and L2 apart from this XY plane?
Yes.
Yes.
What is that plane which is parallel to L1 and L2, which is a subspace? Remember, it should be a subspace.
No, then nothing.
Same, can you tell a subspace which is parallel to L1 and L2 here? Line passing through origin, which is parallel to L1 and L2 apart from
Only
U.
you. Nothing.
Only U, right? So what is your guess then?
Yes.
This
It's
U
unique.
in this representation must be
Unique.
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 Okay. So the subspace U corresponding to an affine subspace L is equal to V plus U is unique. Okay. So that is, suppose the affine space L can be defined as L is equal to V plus U and L is equal to V dash plus U dash. That is, you are having two different representations. Then you should be able to show that this U and U dash are same. Okay. So how do we show that two sets are equal? So you say that U contained in U dash and U dash contained in U. If you can prove this, then you know that U is equal to U dash. Right? So let us try to do that. So let you take some element from L. So some element from L is of the form V plus U. So maybe I'll write V plus U belong to L where U belongs to U. Okay. Now V plus U also belongs to this kind of a representation. So this means I can write V plus U as V dash plus U dash for some U dash from U dash. Correct? So now what is that we can see here? So one more thing. Remember, your V dash is nothing but V dash plus 0, where you can observe this 0 as an element of U. So you can write this belongs to L. All the time this V dash, whatever this V or V dash you are having, this always belongs to L. Remember that. So you can visualize it in this way. Okay. So this means that V dash is equal to V plus U1 for some U1 in U. Okay. Now this implies V dash minus V is equal to U1 belongs to U. Okay. So now what you have done? U dash. What is your U dash? So here is your U dash. U dash is what? U dash is U minus V dash minus V. Correct? U dash is, maybe I will not write implies here. So V plus U is equal to V dash plus U dash implies U dash is equal to U minus V dash minus V. Correct? Yeah.
Yes, ma'am.
Now you know that this is an element of U, and from here you know that this is also an element of U. So this is an element of U. So you started with U dash as an element of U dash, and then you proved that U dash belongs to U. So what does that mean? So U dash belongs to U dash implies U dash belongs to U. What does that mean?
Both are equal.
U dash is a subset of
U.
U. Okay. So the same procedure, you can just replace U and U dash position and try the same proof, and you can see that you can similarly obtain U is a subset of U dash. Okay, so you know that U and U dash are same. Okay, so always in the representation L is equal to L, you have one part which is V and another part U. So this is not unique. In fact, it is any element of L. And here, this is unique. So here, I am assuming that U is non-zero. Okay. So this is not unique and this is unique. So up to this, is everything clear for everyone? Yeah. Okay.
Yes, ma'am.
So how do you define the dimension of an affine subspace? So if you have a affine subspace L is equal to V plus U, then dimension of L is equal to dimension of the corresponding subspace U. Okay. So dimension of L is nothing but the dimension of the corresponding subspace U. Okay. Fine. So now let us look at all possible scenarios, affine subspaces of R2. We already know what are all the possible subspaces of R2, right? So either it can be the zero subspace, or it is any line passing through origin,
Ma'am, can
or
you
it is
explain
the
that
entire space. Yeah.
dimension of L equal to dimension of U? Can you explain that Y equal to X using that subspace and affine space?
Okay. So what is the dimension? That is what we were going to do anyway. So here, what is the dimension of U?
X 1
What is the dimension of U?
1.
1, right? So if dimension of U is 1 and L1 and L2 are V plus U form, so you can say that dimension of L1 and dimension of L2 both are 1. Okay, same you can say here also. So here, what is dimension of U?
It's 2.
2.
So this means that dimension of L1 as well as dimension of L2 is 2. Okay. Fine.
Okay, but we had one element. Come down, ma'am. Come down.
Yes, we are adding one element. That does not change the dimension of the space. So here, remember, this is not a subspace first of all. So this is how we are defining the dimension. So this is how we are defining.
Yeah.
So the dimension of L is defined in this way. Okay.
That V.
Yeah.
What about V? What? Whether V is included? Yeah.
See, this is just a translation. The plane is remaining a plane. The plane is not becoming into a space in R space like R3. The line is remaining as a line only. So so it is not changing into a plane. So you can see that the dimension cannot change from this view itself. You can see that line is just remaining as a line and not changing into a plane. So plane only has dimension 2 and lines are always having dimension 1. Same way here you see that a plane is just translated into another plane. It did not transform into R3 or anything bigger than a plane. So the dimensions are remaining the same. That is how we are defining it first of all.
Okay.
Okay, fine. Okay. So now these are all the possible subspaces of R2, and we know that the translation of any of this subspace is an affine subspace. So first of all, what about the translation of the zero subspace? It will be a point affine subspace. It means it is just a non-zero point from R2. Okay, so any non-zero point from R2 is an affine subspace of R2. Okay, and any line, you know that, so any line x comma mx, that will be translated to mx plus c, right? So a line parallel to that. So any straight line, okay, any straight line if you consider of the form y is equal to mx plus c, then you know that that will be an affine subspace. And what about the translation of entire R2? What will be the translation of entire R2? So you have the set of all x comma y in R2. Sorry, x comma y in R. Now, what will be translation of this set? You take any translation, maybe x plus a, comma y plus b. What is this set?
Still R2.
Still
Still
R2, right?
R2.
So both are still R2. So the translation of R2 will be just R2 only. So what are all the possible affine subspaces? Either it is a point from R2, or it is just any straight line from R2, or it is just the entire space. So these are the only possible affine subspaces of R2. Same way, let us look at the subspaces and affine subspaces of R3. You know that zero subspace is an subspace of R3, and then any line passing through origin, okay, so which is spanned by only one non-zero vector, and any plane passing through origin which is spanned by two non-zero linearly independent vectors, and then the whole R3. So these are all the possible subspaces in R3. Now what are all the translations which contributes to the affine subspace? As usual, the zero subspace translated to some point in R3. So any point in R3 is an affine subspace. Okay, and then any straight line. Okay, any straight line you consider, that will be a affine subspace. Similarly, any plane is again an affine subspace. And then of course
Ma'am,
the entire R.
why,
Yeah,
ma'am, why is the line, any straight line is a subspace of R3? Can you explain this point, please?
any straight line is, see, any straight line passing through origin is a subspace, right? This is week 3 topic maybe. So what is your doubt here? Why any straight line is passing through origin is subspace?
Okay, okay, ma'am. Okay, ma'am, I get that.
Okay, any straight line passing through origin particularly. So without this, it cannot be a subspace. But when you go to an affine subspace, it is just any straight line. So passing through origin, I am not putting here. Okay.
Okay, ma'am.
Similarly, any plane passing through origin is a subspace, and just any plane means that will be a affine subspace. So similarly, here the translation of entire R3 will be just R3. So these are all the possible affine subspaces of R3. Okay. So for example, if you see a plane like this, the translation is another plane. Okay. So the points, all the points will be translated. Okay. So we have seen what is an affine space. Okay. And affine space is not a subspace. So how do we add elements, two elements from an affine space? Because you know how addition and subtraction are defined in a subspace, but now we are just in a subset of the vector space. So how are we going to define addition and scalar multiplication on affine subspaces? Okay, let L is equal to V plus U be an affine subspace. Let L and L dash be two arbitrary elements of L. Okay, so we are taking just two elements from L, and what is the sum of these elements we are going to see. So let us write L as V plus U and L dash is V plus U dash for some U and U dash in U. Okay, so now, so here we are defining, so this is vector, not vector, affine addition. So here what we are doing is affine addition because we are taking two elements from an affine space. So this is from L and this is from L. Okay. So now you have two elements from L, and how are we going to add? You know how addition works in a subspace. So only this part is fixed. So we are going to add the elements of the subspace alone and leave this vector V as it is. Okay. So V plus U plus V plus U dash is defined as V plus U plus U dash. So I am just keeping V as it is and adding only the elements of U. Okay. And similarly for scalar multiplication, I'm going to do the same. I'm going to keep V as it is and I'm going to do the scalar multiplication only with the U part. Okay. So now we'll look at an example, then it will be more clear. So consider the affine space. So this is what the example we considered earlier also. So we are considering L is equal to 0, 1 plus U, where U is this space. So that is a set of all x, 1, where x is in R. So according to this way of addition, so L1 is 0, 1, so plus x1, 0. This is some L1. And L2 is another element. Now what is L1 plus L2? So this is your V now. Your V is fixed, right? So let us fix V. And let us add the elements of U. So this is your U and this is your U dash. So I am adding U plus U dash. So V plus U plus U dash. Okay, so for example, if I am having maybe minus 3, 1, and then I am adding it with minus maybe 2, 1. Okay, so minus 3, 1, how can I express it in this form V plus U? 0, 1 plus, what is your U?
Minus 3,
Minus 3, 0.
Right? So this is your view V and this is your U. Plus 0, 1 plus, what is your element from U?
2, 0.
So V, this is U dash. So now you know that this is V plus U dash. So what is your V? 0, 1.
0,
Comma one.
And then U plus U dash is minus 1, 0. So the final answer is minus 1, 1. Okay, you understand how we are doing this fine addition? It may look very
Yes,
Yes,
ma'am.
ma'am.
different, but I hope you understand.
Ma'am,
Yeah?
I don't. Can you graphically show what it means to add to affine subspaces? What would it look like?
Adding two elements of an affine space.
Wait, are we adding two elements or are we adding two affine spaces?
No, we are just adding two elements from affine space. So this is an element, one element from this L, and this is another element from L. Okay? Fine?
And what did we do to them then? Wait.
See, here we are just going back to U and then we are again adding this V part. That's all. So maybe here let us take this example here. So you are having, this is your U. Let us say this is your U. Okay, so U is set of all x, 0. X is in R. Okay, now this is your L. So your L is set of all x, 1 such that x is in R. Okay. So now I'm adding two elements, minus 3 comma 1. Maybe I'll take this as minus 3 comma 1. Okay. And the other element is 2 comma 1. So what is 2 comma 1? So this is your 2 comma 1. Okay. So minus 3 comma 1. And what is here? 2 comma 1. Okay. So now what are the elements corresponding in U here?
Minus 3 0,
Minus 3 0. And here
2 0.
2 0. Now what is the sum of these two entries?
Uh, minus 1 0.
Minus 1 0. So this is your minus 1 0. So again you go back to L here, minus 1 1. So the sum of these two entries is this. So I am coming to U and then going back to L in this way.
This makes sense.
Got
Thank
it?
you.
Okay. So the same way we are doing scalar multiplication as well. Okay. So if you take L is equal to some element from L, then CL, you know that it is C, you are multiplying the C only to this U part. So for example, if I am having some element, let us say L is equal to maybe minus 1 comma 1. Now what is 2 times of L? So 2L means, first of all, L I should write it in the V plus U form. So V is here 0 comma 1 plus minus 1 comma 0. So this is your V and this is your U part, right? So I'm multiplying this 2 only here. So it means 0 comma 1 plus minus
Minus
2.
2 comma 0.
So it is minus
Minus
2.
2 comma 1.
2 comma 1.
Okay, so you understand how addition and scalar multiplication works in affine spaces? Yeah?
Yes.
Okay.
Yes, ma'am.
Okay. So now let us look at an example. Consider the affine space L of R3 defined in this way. Now express it as V plus U for some subspace U of R3. Now this is a common rule for any plane. So remember this, or you can understand it also. So if you have any plane like this, AX plus BY plus CZ equal to D. Immediate. So this is an affine space. You know that this is an affine space. What is the corresponding subspace?
0 equal to 0.
That's all, right? So the corresponding subspace is nothing but set of all x comma y comma z such that ax plus by plus cz is equal to 0. Sorry. Now you have x plus 2y minus z is equal to 5. Now what is the v you can choose? You have to choose a v. So can you choose a v here?
5. Is it 5?
See, v should be an element of R3. So obviously you know what is your u. It is set of all x comma y comma z such that x plus 2y minus z is equal to 0. What is your v? So for v, it is very easy to choose v
5
from this.
comma 0 0 0.
Yeah. So you can make either this as 5 and this 2 as 0, or you can take 0 0 minus 5, anything you can choose. You can choose any vector from L. Okay. So for example, what about who said 5 0 0, or what is it you said?
5 comma 0 0.
Okay. So this entry, it belongs to L, right? Because 5 plus 0 is 5. So you know that you can write L as V plus U. So this V is not unique. Everyone can choose V in different way. V is just some element. You have to choose V. Choose V from L. Okay. So any element from L makes a choice for V. Okay. So L is equal to V plus U. We have done. Okay. Now this is a very important example for an affine space. Okay. So consider this system of linear equation Ax is equal to B. Okay. What happens when B is equal to 0? This becomes a homogeneous system, right? So the solution set is a subspace of Rn. So namely the null space. So when B is equal to 0, what are the solutions of Ax equal to 0 called? So that collection of solution are nothing but the null space of A, right? Now if B does not belong to column space of A, okay, B is not 0 and it does not belong to column space of A, then what does that mean?
No solution.
Ax equal to B does not have a solution. In that case, what is the solution set of Ax is equal to B? It is an empty set, right?
Empty.
Set of all x in Rn such that Ax is equal to B is empty. And in this case, the set of all x in Rn such that Ax is equal to 0, this is nothing but null space of A. Right? Now the next scenario is when B is in the column space of A. You know that when B is in the column space of A, it means there are solutions for this equation Ax is equal to B. Right? We don't know whether it is unique or not unique, but we know that the solution exists. Right? So let V be a solution of the equation Ax is equal to B and U is some element of the null space of A. Okay? Hence, we have A is equal A times of V plus U. What happens to A times of V plus U? AV plus AU. Now, what is AV? So, V is a solution of Ax is equal to B. It means what? AV is equal to B. Right? And U belongs to null space of A means AU is equal to
0.
0.
So, AV is,
0.
and AU is 0. So, you see that this is now again A times of V plus U is now B. This means what? V plus U is also a solution of Ax is equal to B. Got it? So V is a solution of AV equal to B and U is a solution of null space of A implies V plus U is also a solution of Ax is equal to B. Okay. So now in this case, the solution set L is an affine space of Rn. So your L is set of all x in Rn such that Ax is equal to B. Now, in this scenario, when B is in the column space of A, only in this scenario, you know that L is an affine subspace. Okay. So, here L is an affine subspace. And how do you write it in terms of a vector plus a subspace? You know that this is the corresponding subspace. And you choose any solution of this Ax is equal to B. Then that gives you a representation of the form V plus U. Okay. So in this case, this is an affine subspace written in this form. So this is the corresponding subspace for this affine space. So is this example clear?
Yes.
Yeah. Okay.
Yes, ma'am.
Yes.
So here, this is your U actually. So in case 1, you are just getting U. In case 2, it is an empty set. In case 3, you have L is equal to V plus U form. Okay. Fine. So this is an important example of an affine space. Okay. Okay, coming to affine mappings. See, affine mappings are not very straightforward like you understand the linear transformations, because you see, even for defining addition and subtraction in affine spaces, we come back to the subspace and then you again go back to L. To understand that itself, it was not very easy. So affine mappings are not again very straightforward like linear transformations. So here for this course, don't worry too much about affine mappings. We will see, look at the definition. Maybe we'll look at an example also, but don't worry too much about affine mappings. Just know what is affine mapping. Just know the definition. Don't worry too much about it. Okay. Fine. Let L and L dash be affine subspaces of V and W respectively. Okay. So let us take two affine spaces. And the corresponding subspaces here are V and W. Okay. So we are going to define a map from L to L dash. Okay. So how are we going to define? So first of all, here you have L and here you have L dash. So these two are affine spaces. Then you know that they have this kind of a representation. right? So L, first of all, you are representing as V plus U. L is represented as V plus U. So these are not corresponding subspaces, subspaces of V and W. Sorry. So L is V plus U, and here L dash, you want an element from L dash here. So you know that f of V belongs to L dash for any V in L, because f is a function from L to L dash, right? So for any V in L, you know that f of V belongs to L dash, right? Because f is a function from L to L dash. So I'm defining L dash as f of V plus U dash. You just need an element from L dash for this expression. So I'm taking f of V plus U dash. Okay, so U dash is the corresponding subspace for L dash. Okay, so now to define the affine mapping, I have to first of all look at the underlying transformation. Just like we were doing for addition and subtraction, we are going to look at what is going on from U to U dash. Okay, so if the mapping U to U dash defined in this way, G of U is equal to f of V plus U minus f of V. So if this defines a linear transformation, then we can say that this f is an affine mapping. Okay, so if you have any function like this from L to L dash, and then you define G in this way, if this G is a linear transformation, then we call f as an affine transformation. Okay, so this is the part which you need to remember. Okay, so here G is from U to U dash is given. So how to see that this part belongs to U dash? First of all, this part should belong to U dash. That at least this you should understand, right? Okay, now f of V plus U, where does it belong? Where does it belong, f of V plus U? So V plus U is an element of L. So f of V plus U belongs to
L dash.
and L dash, you know that you can write it as f of V plus U dash, right? So this means that you can write f of V plus U as f of V plus U dash for some U dash in U, right? So now you see that f of V plus U minus f of V is U dash, which is an element in U dash. So you see that this function is first of all defined, and then if this is a linear transformation, you know that the given function is a linear mapping. Okay, so for a linear transformation, what is that, you know? What is the definition of a linear transformation?
T of
G of U1 plus U2 should be equal to,
G of U1 plus G of U2.
okay, and similarly G of
C of into some
U is
constant.
equal to C times
C
of
of
G of,
G.
okay. So this is for a linear transformation. Now, what is the similar property you can have for an affine mapping? Okay, so it is not very simple like this. Let us see what it turns out to be. Okay, so now you have f of L1 plus L2. Now, what is L1? V plus
V plus
U1,
U1,
and L2 is
V plus
V
U.
plus U2,
V plus U2. So now, what is the sum of these two elements?
V
V plus
F
U1
of U
V
plus
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 U1,
plus
U2.
U2.
right? So we have just added the two elements, L1 plus L2 now. So now next what happens? Next what happens? Here you have done what is L1 plus L2. What is the next step? Any idea? It's not at all very obvious, but yeah, we have to do some addition and subtraction. Let us do some addition and subtraction to get this form here. You have to somehow get this form here. So here I am going to add and subtract f of v. Okay. So now how can we rewrite the first term?
You can add f of v into it.
So this is like u now. So f of v plus u minus f of v is g of u. So how can you write this entire term now?
G of u plus f of v.
So g of your u is nothing but u1 plus u2 plus f of v. Right? So now you have written this particular part, the first part, this one, as g of u1 plus u2. So up to this you understand? Yeah? Okay. So the next step is I'm going to use this property of g now. So g of u1 plus g of u2 plus f of u. Now again I'm going to write this g of u1 and g of u2 in this form. So f of v plus u1 minus f of v plus f of v plus u2 minus f of v plus f of v. Okay. So now you have minus 2 f of v plus f of v. So what is that you will have? F of v plus u1 plus f of v plus u2 and then minus f of v. Right? So here v plus u1 is nothing but L1 and this is L2 minus f of v. So what is that you have for an affine mapping? For an affine mapping, f of L1 plus L2 is f of L1 plus f of L2 minus f of v. Okay. So this is the first property. And let us look at the scalar multiplication now. So similar way. So this is f of, what is c times of L?
P
V
plus
plus
CU.
cu. Right? Now v plus cu. Now f of v plus cu. Again, I'm doing the same step like before. F of v plus cu minus f of v plus f of v. You know that this part can be rewritten as, can you tell?
G of
Yeah?
G of CU. CU.
Cu plus f of v. Now g of cu, g is a linear transformation. So I can write it as
CGU.
plus f of v. Now again g of u, I can write it as
F
F of B plus U minus F of B.
plus f. I multiplied the c both. Yeah?
Yes, ma'am.
F of v plus u minus f of v, right? Okay. So now the next step is c times of f of v plus u. V plus u, I can replace it with L. And then here you have minus c minus 1 f of v. So what is that you got? F of cl is equal to c times of f of L minus c minus 1 times of f of v. Not at all obvious, right? Only with the calculations you can see this. So affine mappings are not very easy to visualize for like linear transformation. In fact, linear transformations are itself not very easy to visualize. So affine mappings are even more difficult to visualize. Anyway, you can understand the steps here. Whatever I have done, the steps you can understand, right? Yeah.
Yes, ma'am.
Yes, ma'am.
Okay. So we have seen. So given an affine mapping, how to check that it is an affine mapping, we have seen. Now, if you are having a transformation, how can you define an affine mapping? So suppose you have a transformation from u to u dash. Okay, then you fix two vectors from L and L dash. Then you define affine mapping in this way. F of v plus u is equal to v dash plus t of u. Okay, so you can define any affine mapping in this way. Okay, so any affine mapping can be defined in this way. So you can see that t of u is an element of u dash. So now this belongs to v dash plus u dash. Okay, so you see that we have defined a map f from v plus u is an element of L, and you have v dash plus t of u is an element of L dash. So L here is V plus U and L dash is V dash plus U dash. So you have a mapping from L to L dash. Okay. And in fact, if you want, you can also verify that. So this T, when you write f of V plus U minus f of V, maybe it will reduce to this form. You can check that maybe. Okay. So let us look at an example for an affine mapping. So here you have L and L dash. So x comma 1 is x in R. So you have a affine space from R2 and you have another affine space from R3. Okay. So we are writing them first of all as V plus U and V plus U dash. So here this is your V. I'll switch to blue. So this is your V and this is your U. Right? And again, this is your V dash and this is your U dash. Okay, so this is your U dash. Now, according to the notation used in the definition of affine map, f from L to L dash, f of x comma 1 is x comma 2x comma 5. Right? So you have here f of x comma 1. Okay, you are defining. So this is how they are defining a map like this from L to L dash, and we want to check whether this mapping is an affine mapping. Now, how can we check whether this is an affine mapping? You have to check whether this underlying map from U to U dash is a linear transformation. So what is this? First of all, we should know. So U is any element from here. So any element from here is of the form x comma 0. So f of V plus U means, what is V plus U? V plus U means it is x comma 1. And what
One.
is V? What is V? F of V according to this definition. First of all, they are writing only V. V is 0 comma 1, and then they are writing what is f of x comma 1 and what is f of 0 comma 1. X comma 1 is x comma 2x comma 5 and f of 0 comma 1 is 0 comma 0 comma 5. So you are getting x comma 2x comma 0. So g of x comma 0 is x comma 2x comma 0. So is this defining a linear transformation from U to U dash?
Yes, ma'am.
Yes.
So this is defining a linear transformation, and hence this f is an affine mapping. So given an affine mapping, you understand how we are verifying whether it is a linear transformation? You first should know what is your G, then you should check whether your G is a linear transformation or not. So for that, you should be able to express this L and L dash as V plus U and V dash plus U dash first of all. Then only you will be able to understand what is going on here and how to write these things. Okay. So I'm just telling what we have done in affine mappings. Affine mappings. So for affine mapping, you are defining a map from L to L dash. You should have a representation for L and L dash. L is V plus U and L dash is f of V plus U dash. Okay. Then you are defining G from U to U dash in this way. If you can verify that this is a linear transformation, then you know that f is an affine mapping. So this is the definition of affine mapping. Okay. And then it has this property that f of L1 plus L2 is f of L1 plus f of L2 minus f of V. And you have f of CL is C times of f of L minus C minus 1 times of f of V. Okay. And you have an example here. Okay. So up to this, you understood whatever I have told you, right? Yeah.
Ma'am, actually I missed this part. This x comma 2x comma 5 was already given, or like?
So this is given. So this is given.
Acha, okay.
This part is given. We are verifying whether, so here we are verifying whether this f is a affine mapping. That is what we are doing here.
Okay. Yeah. Acha,
Okay.
yeah.
Ma'am, can you explain the example but once more?
Okay, so here first of all we have L and L dash and we are writing it as V plus U and V dash plus U dash. This part is fine, right? Yeah. Next, we
Yes.
are going to define, we are given a map f from L to L dash in this way. We are going to verify whether this is an affine mapping. So according to the definition, this is an affine mapping if the underlying transformation G from U to U dash defined in this way is a linear transformation. So we are looking at what is this G first of all. So this U is any element from U. So it is x comma 0. And V plus U means it is just x comma 1. And V is 0 comma 1. So now f of x comma 1 according to this definition is this, and 0 comma 1 according to the definition is this. So the final G of x comma 0 I got is x comma 2x comma 0. And now I can clearly see that this G is a linear transformation from U to U dash, and hence f is an affine mapping from L to L dash. Clear?
Yes,
Yes?
ma'am.
Yes,
Okay.
ma'am.
Yes.
Okay, fine. So maybe you can try this exercise on your own. Meanwhile, I'll have a short break and we'll be back. Okay. Okay, so have you completed exercise 1?
Yes, ma'am.
Okay, what is
Yes,
the
ma'am.
answer? It's very obvious, right?
Action
So
is
n,
Option
Second
2.
option.
Option 2.
okay, x plus. So what is the question? First of all, L is an affine subspace like this. Which of the following subspaces of R3 correspond to the affine subspace of L? Okay, so it should be x plus y plus 2z. This part should be 0. So it is option 2.
Two.
These are also subspaces but not corresponding to this affine space. And this is not a subspace at all. Okay. What about exercise 2? Which of the following subsets of R2 represent an affine subspace of R2? We already have seen that there are 3 possible ways of having an affine subspace, affine space in R2. Okay. So what are they? Do you remember?
Must be linear होते.
Either point
Or
or
a line.
plane
line
R2.
or entire R2. So these are the possible affine subspaces of R2. So now what is this?
This is not a fine.
First of all, what is this set?
Like
This is
Circle with
circle.
same origin and
See,
radius.
x squared plus y squared is 0 here.
It's a point.
It's a point.
What
0,
is that point?
0
Yeah.
origin.
Zero. It's a
Zero.
circle.
Okay. So it is just the 0 space. So you can consider, so this is the subspace also. So any subspace is an
Cannot be entire.
affine space. So you can consider this also as an affine space. Okay. Fine. And what about this one?
No.
This is a circle, so this is not.
Yeah. So
This
this
is circle.
is a circle with the radius 2. So this is not an affine subspace. What about this one? Is this any of these 3? Is this a point,
No.
line, or R2?
One is a polynomial, so it is not.
Yeah. And what about this one?
Yeah, it is
It's
line.
This is a line. So this is a point. This is a line. So this is a affine space. What about this one? Set of all x,
Line.
y,
Yes,
such that x
ma'am.
equal to 1.
Yes, ma'am.
This is a line.
Point.
So this is a
Affine.
affine space. And what about this one?
Parabola.
This is not any of these 3. So this is not an affine space. Again, this one is not any of these 3.
Not.
So this is a point. So this is
Affine.
an affine space. Okay. Fine.
So basically of AX plus B form.
Yes, yes. Line should be ax plus b, or you can have a point or entire R2. Only these 3 are affine spaces of R2. Okay, fine. Now look at exercise 3. Let U be a subspace of the vector space R3 and a basis of U is given by this. Okay, then we first of all, are they linearly independent? These two vectors.
Yes, ma'am.
So what is the dimension of U?
2.
Yeah.
2.
Dimension of U is 2 means. So what is a two-dimensional space in R3?
Line.
2 plane actually.
U is a plane in R3. Okay. Okay. Then which of the following subsets of R3 is an affine subspace of R3 such that the corresponding vector subspace is U? Okay. So it means first we should understand what is U. Okay. So U is the span of 0, 1, minus 3 and 1, 0, minus 1. So now how can we write this? This is,
Linear combination.
yeah, alpha times of this vector plus beta times of this vector. Alpha and beta in R. Okay. So now this can be, we can rewrite as alpha. Alpha is 0. So only beta. And then you have
Alpha.
alpha. And then you have,
Minus 3 alpha minus beta.
okay. So you have alpha, beta in R. Okay. So now if I'm rewriting this with x and y, so if this is x and this is y, here you will have minus x minus 3y x comma y in R. So what is your z? So your z is
minus y minus 3x.
right. So z is equal to minus 3xy in R. So you can also write it as set of all x, y, z in R3 such that x plus 3y plus z is equal to 0. Correct? I'm just rewriting this. So now,
Z will be minus y minus 3x. X is beta and y is alpha.
no, now you have got what is your u. So now we have to compare with the solutions here. So now here the question is, which of the following subsets of R3 is an affine subspace of R3 such that the corresponding vector subspace is U? So for the first one, what is the corresponding U? What is the corresponding U for this? X plus 3y,
3y plus
z is equal to
equal to
0.
0.
What about this one?
X plus 3y plus 2z equals to 0.
What about this one?
X plus 3y plus
X
z
plus 3y plus
equals
z
to
is equal to 0.
And what about this one?
0. X plus 3y plus
X plus 2y plus z
z
is
equals
equal to 0.
So you see that
1, 3, 4.
these three are the correct options, right? Okay. Is this problem fine for everyone? Yeah.
Yes, ma'am.
Okay.
Next.
Sir, what about, ma'am, what about second one is wrong? Why?
So here you have 2z, but here in our answer you don't have 2.
Oh, okay. Okay.
Fine. Okay. Consider a system of linear equations. So you have 1, 2, 3 equations. Which of the following is an affine subspace L of R3 such that if V belongs to L, then V is a solution of the system of linear equations. Okay. So here you have a system of linear equation. So the first equation is minus x plus y minus z is equal to 1. The second one is x minus y plus z is equal to minus 1. Can we consider these two as the same? Yeah.
Yes.
Yes, yes, yes.
So we can
Yes.
just leave the first equation and just consider this one alone. And then you have x plus z is equal to 0. So x plus z is equal to 0 means you have z is equal to minus x. So if I'm substituting it here, what will you get?
Y equal to 1.
Y is 1.
Y minus x is equal to minus 1. So y is equal to 1. So you got y is equal to 1 and z is equal to minus x. So the set of all x comma y comma z such that it satisfies all the three equations. Okay, so A
Second
is
option.
equal to B, maybe
Second
I'll
option.
is equal to, maybe I'll write minus x 1 and minus x in R. So it is this one, right? Clear?
Yes.
No. Okay. Sorry. Okay, so I guess we are done with the affine subspaces part. Right, so for affine subspaces and affine mapping, whatever we have done in class, so that is clear to everyone, right? Yeah.
Yeah, yes.
Okay, fine. So the next concept to introduce what are inner product spaces. So we start with something which we already know. We know what are dot products. So we are going to start with dot products and then we will move on to inner product spaces. Okay. Okay, what is mean by dot product of two vectors in Euclidean space of dimension 2? See, why we are first of all going to inner product. What we have done so far, we have R2. We know how to add two elements. We know how to do scalar multiplication. Okay, fine. Now, how to compare, like what is the distance between two vectors, maybe what is the distance from origin to a vector, and what is the angle between two vectors, how to understand these things. So we are moving further to understand again the vectors in R2 or R3. So from that base, we are generalizing to Rn, just like whatever we have done for vector spaces. Okay, so we already have the Euclidean space structure. There we are going to understand how to understand what is the length of a vector, what is the angle between two vectors. So these concepts we are going to understand first of all in R2 and then in R3, and then based on that we will generalize in Rn. Okay, fine. Okay, let v1 is equal to x1 y1 and v2 equal to x2 y2 be two vectors from R2. The dot product of these two vectors is the scalar computed as follows. So how do we do dot product? X1 y1 dot x2 y2 means x1 x2 plus y1 y2, right? So this dot here is the dot product sign. For example, here you have 1 comma minus 4 dot product with minus 3 comma 2. How do you do the dot product?
-3, -8.
Not comma, minus 3 minus 8. So this is the answer, right? The dot product results in a scalar, right? So you are having one element from V, another. So this is your V. Now your V is R2. So you take one element from V and you have another element from V, okay? And you see that the resulting answer you have in R, okay?
Principle of management আছে তোমার
I guess
না
someone
তো
should,
জেনারেলিজম তুমি কি দিয়েছো প্রিন্সিপাল অফ ম্যানেজমেন্ট আছে বললো
okay. Okay, what is the length of a vector in Euclidean space of dimension 2? So suppose let us say you are having a point here. Okay, so what is the length of this vector 2 comma 3? So you know that a vector 2 comma 3 means usually we consider this line. So this is the vector 2 comma 3. Now what is the length of this vector?
Square root of 2 square plus 3
Root.
square.
Right? So here what is the x value here?
2.
2,
And what is the y value here?
3.
Right? So for any x comma y, so if you have any vector x comma y, so you know that the length of the vector is x square plus y square. So this is based on which theorem?
Pythagoras.
Yes.
Pythagoras theorem.
Yes. So using Pythagoras theorem, we know that the length of the vector 2 comma 3 is square root of 2 squared plus 3 square is 13. Right? So you know that you can find the length of any vector in this way. Now what is dot product of 2 comma 3 with 2 comma 3?
4 plus
4
9.
plus 9.
So you
4
can
Plus
14.
4 plus
Square.
9.
So you can see that the length of this vector 2 comma 3, so length of a vector, maybe I'll write x comma y is nothing but square root of x comma y dot x comma y. Correct? Can I write it in this way? Yeah?
Yes.
Okay.
Yes,
So
ma'am.
the relation between length and dot product in Euclidean space is that length of a vector is square root of the dot product of the vector. So now what is the length of the vector 3 comma 4? Answer is
25.
5. 5.
okay. So in general, the length of a vector, you know that this is the formula, right? Okay. Now what is the angle between two vectors? Okay, so what is the angle between two vectors? So for example, you have two vectors here. How do you know what is the angle between these two vectors? Okay,
Using dot product.
so for that, we are going to again use dot product. So let u and v be two vectors in R2. Then we can compute theta, the angle between u and v, using dot product in this way. So maybe this formula for finding the angle with dot product you have seen already, right? So now u is u1, u2, and v is v1, v2. So when you do the dot product, this is what you get, right? So theta is equal to cos inverse of whatever you have here. So here, what is your u? You have considered u to be 1, 5, and v is 3, 4. So what is the angle between this? Cos inverse of what is u dot v? 3 plus 20, 23. And then here you have square root of the length of this vector and the length of this vector. What is the length of this vector?
26.
So this is what? 6?
26.
Yeah. And what is this?
5.
Of 20.
25 by 5.
25.
Cos inverse of 23 by square root of 26 and then 5. So you have, this is the angle between these two vectors. Okay, fine. Now the dot product of two vectors in R3. So we have seen how to find the dot product of two vectors in R2 and then angle between two vectors in R2. Let's do the same in R3. So in R3, what is the dot product of these two vectors? Can you tell? 2
minus 3.
plus 0 minus 3, which is minus 1.
Minus 1.
So in general, what is the dot product of two vectors from R3?
X1, X2.
X1, X2 plus Y1, Y2
Y1.
plus Z1, Z2.
Yeah. Okay. So now how do you find the length of any vector in R3? The
6
same
5
W.
square root of 4
Square root of 4, 3, 8.
plus 3 square plus 3 square.
So here, what is the answer?
16 plus 9 plus 9.
34. Right? So this is 9. Sorry. Right? So this is the length of this vector. So
Basically,
here,
in the dot product, we are doing just component-wise multiplication.
yes, yes. Okay, so this is 34. The dot product is 34 and the length of the vector is square root of 34. Right? So here also the length of the vector is defined as square root of dot product of these two vectors. And the angle between those two vectors are again, so here is a mistake, u dot u, and here also u dot u. So the length of the vector u into the length of the vector v. Okay. So what is the angle between the vectors 1, 0, 0 and 1, 0, 1? What is u dot v here? So this is u and this is v. What is u dot v?
1.
1. And what is square root of u dot u? Again,
U.
1. And what is square root of v dot v?
1.
2.
Plus 1, 2.
2. 2. Root
Right?
2.
So now root 2 or 2? It's root 2.
It's root 2.
Yeah. So the answer here is theta is cos inverse of 1 by root 2. So what is cos
Root
inverse
2.
of 1 by root 2?
45 degree.
45 degrees.
Right? So you can see that now we have seen what is happening in R2 and R3. The same we can generalize for Rn. So Rn dot product of two vectors u dot v is u1 v1 plus u2 v2 plus etc. un vn. And the length of the vector, what is the length of the vector? Here in this case it is this. And the previous case it was x squared plus y squared. So what is the length of this vector? Can you tell?
Square root of u1 square plus u2 square plus and so on.
Right? So in terms of dot product, it is square root of u dot u. Okay, so which is the same again, square root of u1 squared plus u2 squared plus etc. un square. Okay, so and the angle here is again u dot v by square root of u dot u into v dot t. So theta equal to cos inverse of this. So again, all these concepts are just the same. You have imitated it from R2 and R3. Okay, so this is what is dot product. Okay. Now, what is inner product? So what we have done here, So do you remember we have in R2 or R3, we first understood how to add two vectors, how to do scalar multiplication. In general, we saw, and then we saw the properties of those addition and scalar multiplication. Like you have, you can add u plus v is same as v plus u, right? And then you have, sorry, you have the associative property, and then you had the distributive properties. Those properties you combined and collected together, and that properties together, if a set satisfies, then such a space is called a vector space. That is what, that is how we introduced vector spaces. The same we are going to do for inner products. So now you see that there are certain products, certain properties of dot product. So that properties we are going to collect it and call it as inner product. So any function satisfying these properties, you call it as an inner product. Okay. So an inner product on a vector space is a function from V cross V to R satisfying the following conditions. So let us take UVW from V. Then inner product of V comma V is positive. Always the inner product is inner product of the same vector is positive, right? V dot V is always positive, right? For a non-zero vector.
Yes.
And you
Yes.
see, if it is if inner product is 0, then it means the vector is V. So this is happening only when V is 0. And then you can have the linearity property. So you have u plus v comma w is u comma w plus v comma w. Okay. So the first one, we can call it positivity or sometimes non-negativity, because here we have the possibility of 0, non-negativity. And then here you see you have the linearity in the first variable, and here cu is c you can bring out. So these two are linearity property. And what is this property? uv, the position or interchange,
Take care.
symmetric property.
Oh, symmetry.
Okay, now let us combine these two. If you combine these two, what will you get? So u comma v plus w. Now if I'm using this one, I can write it as v plus w comma u. Now again I can use this one. So it is v comma u plus w comma u. Now again going back to this form, so I can write it as u comma v plus u comma w. So you see that linearity holds for the second position as well. The same you can see for this also. So you have u comma cv. Now I'm using property 3. So it is cv comma u. Now again I'm using 4. So it is c times of v comma u. So this is, yeah, so I got c times of u comma. So you see that the linearity property I'm having for the first position as well as the second position. So property 2 and 3 together, this and this together, okay, I'm calling it as bilinearity property, because the linearity is there for first as well as the second position. That is bilinearity property. So positivity or non-negativity, and then symmetric property, and these two bilinearity you have. Okay, so if all these properties are there for a function from V cross V to R, then that function is called an inner product. Okay, so now a vector space together with an inner product is called an inner product space. So you have a vector space, you have an inner product. So now we are introducing IPS. What is inner product space? So it is a vector space combined with an inner product. So if you are able to define an inner product on a vector space, then you get an inner product space. Okay. So inner product space is again the same V, but here you have another function here. Inner product is there. Okay. So this is just V, and this is V together with the inner product. Okay. So already we know that dot product is an example of an inner product. In fact, this only we consider it as a motivation, right? So this is the dot product. Of course, in dot product, what is u dot u? U dot u is simply u1 squared plus u2 squared plus etc. un squared. So it means it is positive for all u non-zero And you know that u dot u is 0 if and only if u is 0, right? So the first property, is it obvious for dot
Yes.
product? And what about the second one? So what about u plus v dot product with maybe w? So you have u plus v means u1 plus v1 you have here. So u1 plus v1 into w1 plus u2 plus v2 into w2 plus and so on un plus vn into wn. So now let us split and write u1 w1 plus u2 w2 plus etc. un wn. And then you have v1
W1.
w1 plus v2 w2 plus etc. vn wn. So now the first part is nothing but u dot w and the second part is v dot w. And what is the third one? Third one is very obvious. You just have to shift positions. So you know that this is u1 v1 plus u2 v2 plus etc. un vn. You can write it as v1 u1 plus v2 u2 plus etc. vn un. So this is nothing but p dot u, right? And what is the fourth one? C times of u. So it is, C times of u into v. So you have CU1 V1 plus CU2 V2 plus etc. CUN Vn. So C you can take commonly and then you will have U dot V. Right? So all these properties are satisfied. So you can clearly see that dot product is an example of inner product. Right? So here is another example. So here U comma V is defined in this way. So the given function is an inner product. Hence R2 is an inner product with respect to this. See, just like you can define addition and scalar multiplication in vector spaces in different way, inner product also can be defined in different ways, not necessarily dot product. So here you have an example. So here, for example, what is the dot product of what is the inner product of, maybe I'll write 1 0 and 0 1 according to this definition. So this is u1, this is u2, v1, v2. So according to this definition, what is the inner product? u1, v1 is 0. u1, v2 is
One.
1. And u2, v1 is 0. And then what is u2, v2? 0. So the answer is -1. But what is the usual dot product here?
0.
0. Right? So the usual dot product is 0, but here you see that when you define inner product in this way, you get a different answer. By the way, here it's an important thing that by an usual inner product, what is called an usual inner product?
Dot.
Dot product is called the usual inner product. Okay, so if you see usual inner product, it is nothing new, it is just the dot product. Okay.
Dot product satisfying those four properties, right?
Yeah, that is what I have explained here.
Yeah. So that becomes the inner product. Right?
Yes. So this is an example of an inner product. Okay,
Yeah.
fine. And here maybe I can assign it as an homework.
That should be 1 plus 1, right?
Which one?
The one which you solved right now. Yeah.
Here
This
there is a minus.
Acha, yeah.
So homework. Sure. So prove that 2 this is an inner product on R2. Okay, so you have to verify all these 4 properties for this. Okay, so you have to maybe do some calculations to verify the properties. So try whether you are able to verify this as an inner product. Okay. So the next concept is norm on a vector space. Okay. So norm usually refers to distance. Okay. So it kind of or distance, or it measures distance. Something which measures distance. Okay. So a norm on a vector space V is a function V to R. Okay, so it takes a value, it takes a vector from V and gives out a real number as a value. So if this function should satisfy these three properties. So the first one is the triangle inequality. So the first one is the triangle inequality. So norm of x plus y is less than or equal to norm x plus norm y for any x, y in V. And then scalar times x, the norm is modulus of x. So this is mod x, mod times modulus c. Modulus c times norm x. Okay. And then the last property is the positivity or non-negativity. So always this is non-negative, and it is 0 only when the vector is 0. Okay. So the length is an example of a norm on vector space Rn. Okay. So obviously, what is the length of a vector in R2, for example? So x, if I am writing as x1 comma x2, what is norm x? Square root of
x1 plus
square
y
x2
x2
square.
square.
right? You know that this distance is always non-negative, and the distance is 0 only for the 0 vector, right? And what happens to norm c times of x?
C.
C here will become modulus here, because you are taking it out of square root. Here that will become modulus sign here, right? So you can see that length is an example. So this is length. So in R2 I have written, in general for Rn also it is an example of a norm. Okay, so in Rn means, so here your V is Rn. So norm x is nothing but square root of x1 square plus x2 square plus etc. xn square. And this norm satisfies all these three properties. Okay. So now, what is the relation between norm and inner product? Why we suddenly are talking about norm here? There should be some relation, right? Okay. So let V be an inner product space with inner product like this. The function norm from V to R defined by norm of V to V is a norm on V. We have already seen this relation for dot products. So what is this? We were able to write this as square root of x dot x, right? So norm of x, the length of a vector, we were able to write it as square root of x dot x. So the same is the relation in general. So norm of any vector, okay, we can define it as square root of v comma v. So whenever you are having an inner product, from the inner product itself, you can arrive the norm in this way. Okay. So now you see you have an inner product. So you can define norm as square root of inner product v comma v. Okay. And this will satisfy all the three properties of a norm. Okay. So, and this norm is called the norm induced by the inner product. Okay. Fine. And here is an example of another norm. So sometimes this is also called the one norm. Okay. So here this is norm u is mod u mod u plus mod u2 plus mod un. For example, if your u is 1 minus 2, 3. According to this norm, what is norm u? Mod 1 plus mod minus 2 plus mod 3. What is the answer? 1 minus 2 plus 3. 1 plus 2 plus 3. The answer is
6.
6. Okay. But what is the usual norm?
Square root of
Square root of u1 square plus u2 square plus u3 square. So what is the usual norm for this vector?
Root 14.
14. Square root 14.
Root 14. Square root 14.
Okay, so this is the usual now. Okay, so you see that first of all, we introduced what is dot product, and then we introduced what are inner product. Inner product means something which satisfies all the four properties. We saw that dot product is an inner product, and there can be several other dot products. Here is one such example. And then we introduced what is a norm on a vector space, and then we saw that the length we already which is already introduced is an example of a norm, right? And then here is another example of a norm. And then we saw that how can we induce a norm from a given inner product. Okay, so that also we already have the relation between dot product and the distance. So from that we have the link here. So norm is nothing but the square root of inner product v comma v. Okay, so these are the concepts in week 7. I guess we are done. Yeah. So what are the things we have seen today? We revised what are equivalent matrices and similar matrices. Then we saw what are affine spaces, then affine mappings, and then we saw what is dot product, and then inner product, and then norm. So these are all the topics in week 7. Okay. So now if you have any doubts, you can ask. So far, is everything clear first of all?
Yes, ma'am.
Okay.
Yes, ma'am.
Ma'am, how do we get this class note?
As usual from the drive. See, if you open the calendar, do you see the link of the Google Sheet or not?
Yes, ma'am.
Yes,
And
ma'am.
open the Google Sheet. If you open the Google Sheet, do you see live session notes?
Yes, ma'am.
Just click the link. It is like we are in week 7. Please, everyone should know this. I'm feeling very sad to hear this question every time. Okay, fine. So, are you able to see it, Swaroop? Yeah? Yes or no? Okay.